Okay, we have used Newton's second law in deriving the solution to the bungee jumping problem, where a person jumps from a balloon, stationary balloon, and would like to estimate the terminal velocity. There are some other laws, apart from Newton's second law, that are basis for understanding of some mathematical models. One of this is conservation laws. Conceptually, conservation law can be written as the change is simply increases minus decreases for any physical phenomenon. This could be applied to our bungee jumping problem, where we have two forces, as you might remember. One was the gravity, the other one is about the air resistance. So in that case, the change in the force is going to be the difference of those forces. If the change is zero, now, by the way, by examining this change, actually we are trying to understand the transient behavior of the system, or time variable. Time variable computation of the parameters in a system, so-called transient. If there is a balance, if there is no change, which means that this equation is zero, then the increases equal to decreases, which is the balanced condition. And that is called steady state calculation, opposite of transient, widely used in many engineering problems. So these two different states or state of a system can be somehow formulated through this conservation's law. On the right-hand side, you can see a pipeline where that is actually a junction of pipelines. There are two inputs and two outputs. If there is an incompressible fluid inside, then the flow entering to this junction and flowing out from this junction could be simply formulated as the sum of the inputs minus sum of the outputs. So if there is a change, then there is a transient situation. And if there is no change, if these are equal, then that's going to be steady state, which means that there is no flowing. In here, for example, this is 80, this is 100, 180, so 120, then this should be 60. If there is a balance, if you would like to get a balance, then there should be 60 out, flowing out in here. Now, let's go back to our bungee jumping problem. As you might remember, there were two forces there. One is downward, the other one is upward due to the resistance of the air, and then gravity. And if there is a balance, then these two forces are equal. So mg is equal to CD v squared, and then we can write the velocity in terms of the mass of the body, the acceleration of gravity, and then drag coefficient. So that is the steady state condition, which means that the person after jumping somehow at a time instant t, he or she will be stationary. So how do we use conservation laws in electrical engineering? There are some other examples in other engineering disciplines. Here we look into only electrical engineering applications, and I'm sure that you know two examples shown on the right-hand side. This is a typical electrical circuit where there are two loops, and we have some node here, okay? And we can use conservation laws in this circuit. If we look into the nodes in here, there is an input current here, an input current here, and output current here. Then if there is a balance, sum of these currents should be zero, which means that that is the steady state. On the other hand, for voltage balance, we can take a look at one of the loops here and take a direction of current and determine the voltage values across the resistors in here and equate this to the supplied voltage. If the difference is zero, then there is a balance condition again. So we simply use conservation laws in electrical engineering. So now what are we going to cover in this course? I just want to list them in two slides here. In part 2, we'll have roots and optimization. Roots is about calculating x values where any function f of x becomes zero. On the right-hand side, you can see this. Optimization is about calculating or estimating x values such that the derivative of the function becomes zero. So on the right-hand side, you can see a smoothly varying function, f of x, with x. And the function becomes zero exactly here and here, which are the roots of the function. On the other end, the function becomes maximum and minimum here. So these are extreme values, and that they can be obtained by taking the derivative of the f of x and look into where this derivative becomes zero. I'm sure I've got a problem with my nose. Part 3, linear algebraic equations. Here we are given a set of equations with several variables. If there are two variables, then there should be two equations, and solving of these equations will be somehow, if it is linear, then this will be somehow finding the intersection of lines. So one line can be an equation. The other one can be written as an equation. So intersecting of these two will give us the solution, actually. Another application is curve fitting or interpolation. In interpolation, we are given two values of any function and we'd like to estimate the value in between these two values. So what is the value in here? So let's say that's x1 and x2. Let's say x 3, then what is x3? Given that x1 and x2. So fx1 and fx2. This is interpolation. Regression is about how to fit a line into some samples, given samples. Suppose that we conduct a measurement, collect some data, and put those data on graph and look into how we fit a line to this data. Here, you can see the illustration. This line may be fitting well with those data. Okay, and the last two will be integration, differentiation, and differential equations. Integration and differentiation are very important subjects in engineering. Basically, if we take a function, let's say f of x or y, then the integration is simply the area under the function within a range, let's say x1 to x2. So that is simply x1 to x2 f of x dx. On the other end, differentiation is simply the slope of any function or curve at any point. Here, for example, let's say x3. So this slope is simply the differentiation of this function. So the f of x dx. As we have shown in previous slides, Euler's method is commonly used to estimate the values of a function iteratively, where we need slope of the function. Differential equation is can be given simply with a function f t y. So variation of y as the time varies, and as we have shown in previous slide, if we use computational methods, numerical methods, this differentiation, first order differentiation, gives us the slope, and using the slope, we can estimate the values of the function. So all this will be covered in this course.